Okay, first, can everyone hear me fine? Thumbs up at the back. Okay, good. I have a slight tendency to talk fast and a little quiet, so please do feel free to interrupt me at any time. Okay, so model-based RL, I'm going to go over some pretty basic stuff in model-based RL. This is very much going to be a standard lecture. And as part of this lecture, I really want you to ask questions. This is a summer school after all. I'm going to try very hard to stay within the allotted time as well, so I have some extra slides at the end that we will or will not get to. And I'm going to give a few chances for you guys to solve some exercises also. So really my main goals for this, by the end of this lecture, I want you to get just a few basic things. I want you to understand how we can use models to learn optimal value functions and policies. I want you to really understand one strategy that I think is going to be part of the solution in some way, and that's the strategy called Dyna. And that's for the online setting where we have data coming in a stream. And then I want you to understand that there's just a few other ways that you actually could use models other than this one in-depth strategy that I'll tell you about. Okay, so that's my goals for you by the end of this lecture. Okay, first, what is model-based RL? Okay, I like to think of there being two situations where you care about model-based RL. You might imagine a model-based RL is when you're given the model, and you might imagine model-based RL is when you're learning the model. Okay? These are both have a model, whether you learned it or were given that model, and the question is still going to be how are we going to use that model as effectively as possible. For the purpose of this lecture, I'm going to talk a lot about what do you do with a learned model. I'm a person who cares a lot about online learning, so I want the agent to interact with the environment and to learn as much as it can on its own. But towards how are we going to do model-based RL with a learned model, we're going to start off just with a brief review of what would you do if someone gave you the model. Okay, so we're going to start off in this offline setting. So as a high-level outline for the topics we're going to cover, first I'll just tell you a little bit about how would you use a model if someone gave it to you and you could learn offline. Then we're going to move to how do you do learning with models in the online setting. And so there I'm going to particularly tell you about Dyna. And then finally I'll just give you a few other ways you could have used the model. Okay, so we're kind of going to be stepping through this outline. Let's start here. Okay, so let's imagine that someone handed you the transition and reward dynamics. So for a given state and action, you can ask your model, what's the distribution over next states and rewards that I could see? You guys should be very comfortable with these transition dynamics at this point. So if someone handed this to you, they've essentially handed to you everything you need to know about the world. You don't even have to bother interacting with the world. Just offline, you could go ahead and solve for what is the optimal policy or learning for policy evaluation. So here, for example, you've seen Bellman equations already, but we could go ahead and just solve this Bellman equation. So I'm not sure if you've seen specifically this Bellman equation, so let me just tell you exactly what it's saying. Here it's saying that for some state in action, this Q star SA is supposed to be telling you what is my expected return if I took this state and then took this action and continued following the optimal policy from there. So that tells you in a state, if action 1 has higher expected return than action 2, then you should be taking action 1. So if you have this Q star of SA, you can just act by taking the maximal actions according to this function. Okay, so here this Bellman, you guys have already seen this Bellman equation, but this Bellman equation is saying if you're actually able to get Q star that satisfied this, it's telling you here that this max A, this is the reward you would receive immediately from state S taking action A, and then if you were to take the best action you could in the next state and were to do this forever onward. Okay? So there's lots of nice algorithms for solving these Bellman equations. Here you need the model to actually solve this equation, and you might do something like value iteration. So actually Pascal just talked about value iteration for POM-DPs, but here you can think about it if you actually had the state. So here the idea is just I'm going to have a current estimate of my Q values, let's say on the kth iteration of my value iteration algorithm, and I'm going to get my next estimate just by computing this formula for all states and actions. So just looking at this in pseudocode, so you can see it in two different ways. You would just do something like initialize your Q values to some initial guess. You don't really know at all what your Q values are supposed to be, so we'll just set them to 0 here. It doesn't actually matter what you set it to. And then we're just going to loop through all states and actions. We're going to apply this formula that you just saw, this Bellman equation. We're going to update what our current Q value estimates are, and we're going to check is the max difference for any state in action above some threshold that I think is acceptable. So here you'll pick some threshold theta. If you've looped through your last set of states and actions and your Q values have not changed, you've reached this fixed point and you don't need to keep going to get the fixed point to your Bellman equation because you're done. Okay, so then that means you've gotten your Q star, and now we can just output our optimal policy pi star. Make sense? Okay, then that's essentially what we would probably like to do if we had our models offline. Now there's other people who are, there's of course other smart ways to use given models, even in an offline setting, but a lot of algorithms are based on something like value iteration. Okay, that's really all I'm going to tell you about the offline setting. So the reason I want you to know about that algorithm is actually we're going to use a very similar idea in the online setting. We're still going to want to do something like value iteration, but things are going to change a little bit when we're gathering data and because we have approximate models. Okay, so yeah, here what I'm saying is we're going to use a similar approach, but it's going to be online. Okay, so now I'm just going to start getting you to think a little bit about how this looks different in the online setting. So you've seen this picture many times, but the agent's interacting with the world. It's seeing this sequence of states and actions and rewards. And you can sort of think of this like the agent is gathering these tuples of experience, or this data that we have on the side. And for any one tuple here, it could do something like a Q-learning update, state, action, reward, and next state. And so it is sort of approximating these Bellman equations, but just from a stream of data in a completely model-free way. Okay, so in an online RL without a model, you've seen Q-learning quite a few times now in this summer school. This is sort of what we imagine it looks like. The agent gets some tuple of data from interacting with the world, and then it does one Q-learning update, and then it just throws that sample away. Okay, and then it's going to see another tuple of data. It's going to do a Q-learning update, and then it's going to throw that away. Okay, so that doesn't seem like a particularly sample-efficient thing to do. Instead, a much more reasonable strategy might be something like taking that tuple of data and trying to learn some model about the world, squeezing as much juice as you can out of that data, and then using that model to try to update your policy. Okay, and so one goal that we're going to have when we do model-based RL is, instead of just using these samples in a completely incremental way, how can we take those samples and convert them into a form that we're going to call a model that lets us learn from those samples as much as we can? There are actually other reasons you would want to have a model as well, but this is going to be my focus. Okay, so then we might ask, now we're moving to learn models, where we have this little model component in our agent. What are actual possible learn models? Okay, the most obvious answer is we just talked about value iteration for the offline case. Well, we could just try to learn the actual transition dynamics from our data and then do similar things like we did in the offline case. Okay, so the most obvious answer is let's go learn some p-hat that's trying to do the best job it can modeling our transition dynamics. And we have a whole fields of machine learning dedicated towards learning functions and learning distributions. Okay, so we should be able to leverage all of that to go learn these models and do better. Realistically, what we're going to end up doing is some kind of abstraction, but we're going to get later to what kinds of models we can learn. And for now, let's just assume we're going to try to approximate these transition dynamics, some p-hat. Okay? So that's the world that we're in right now. Our agent's learning in an online way. It's trying to approximate p-hat. And now it has the question of how is it actually going to use that p-hat? Okay, so when we're moving to this using learn models, I'm going to propose that we use this framework called Dyna. It's a very widely used framework. So first I'm going to tell you what is Dyna. Then I'm just going to explain to you one simple instance of Dyna that's something you may have heard of. That's called experience replay. Then we'll go through a couple of choices that are really important in Dyna. Actually, the two key choices, which is what model should you pick, and how do you do this thing called search control, which I will tell you what search control is. Okay, and then we'll talk about a few choices for those two really important components. So I have a part 1, part 2, and a part 3. Almost the entire lecture is this part 2, which is why it has its own little sub-outline. Okay, good. So by the end of this part, you should know what Dyna is, and you should know what these two key things are and some options for them, or some strategies for them. Okay, so what is Dyna? If you'll notice, the name Dyna looks a little bit like dynamic programming, and it is going to be like a dynamic programming algorithm. Okay, so we have our usual, sort of agent environment diagram. We have an environment here. We have experience going to our agent that has a policy and value function. And usually what we imagine is we do these kind of direct RL updates. Okay, and now in Dyna, there's just going to be an additional step where we're also going to take that experience. We're going to learn a model. And then in the background, we're going to do some simulations from that model as if it's the real world. And we're going to do simulated updates with that. We're going to do updates with that simulated experience. Okay, so here, for example, we might do updates in the real world using rewards and states we actually saw in the real world. And here we might go ask our model from some state and action. You could hallucinate some state and actions, or you could use real states you saw. And then you're going to ask your model, what's a possible next state and reward? And then you're going to pretend like this was actually a tuple that you got from the real world. And you're just going to go ahead and do a regular Q-learning update. Okay, and you might do many of those planning updates in the background. So the key idea is very simple. If you've learned a model, you're just going to use simulated experience from the model as if it is the real world. And even though this is a very simple idea, it's one of the main things I want you to get out of how could you do planning with learned models. So we're going to revel in it a little bit and go through some pseudocode for this. Okay, so how might this actually look if you were to go ahead and use Dyna? Oh, do you have a question? How do you initialize the model or the Q values? So right now I haven't told you anything about what your model architecture is going to be or how you would initialize your model. This here just says we're going to initialize our model somehow. So I guess I'm telling you I don't know how you're going to initialize your model. If we were to jump ahead to the learn models part, we're going to talk a little bit about learning models. The best way to initialize your model is if you had some prior information for your problem. Maybe you could actually put that information into your model and initialize. How do people actually do it is usually the standard ways that we initialize our functions in machine learning right now. Some kind of randomized strategy that seems to work well for optimization.
What do you mean by simulation that differs from the interaction with the environment? Is it something that generates samples in the event space, or is it a real simulation, or is it from like recorded data form?
Great question. The question was, what do I mean by simulation? Do I mean, maybe I'll just summarize it with what do I mean by simulation. I really mean that the agent has a model inside its own head, and it's simulating experience from that model. An implicit model was happening in the environment. You can imagine that the agent is asleep even, so that there's no interaction whatsoever with the world, and it just gets to simulate any experience it would like to in its head. It can imagine, oh, I wonder what would happen if I was at the ice cream store and I took the action buy mint chocolate ice cream, and what would be the outcomes, next state, and reward. So it could be perfectly separate from whatever's happening around it right now. And then contrasting with a simulator, sometimes we use simulators as the real world. If you were to give the agent an actual simulator as an internal model, I would count that as the first part of this talk, which is someone handed you the real model. Okay. Any other questions? Okay, good. Okay, so how's DynaQ going to be actually implemented? Here we're going to imagine you initialize your Q values in your model with some strategy. So before we initialize our Q values to 0, you could do something like that again. And then we're just going to interact with the world forever like we usually do. The agent's going to take action, say according to its current Q values. It's going to do a regular Q learning update on the real world experience. And then it's also going to update its model with that real world experience. Okay, and then we're going to ask our model for some state, and we're going to choose some state in action. We're actually going to call this search control, but we're going to choose some state in action. For example, you might randomly choose data you've seen before. You can also hypothesize interesting states and actions your agent could take. Here, this is just a basic choice. Then you can ask your model what's the next state and reward, and do a Q-learning update on that simulated experience. Okay, and then we can just do this many, many times in the background, and times if we would like to from our model. Okay, good. Took that very simple idea and explained it to you somewhat ad nauseum, but hopefully you understand what the Dyna is now. Go ahead.
So the model here can either be a genetic model can either be a parameterized model, but it can also be a memory buffer.
Great, so I'm going to tell you about how experience replay, so a buffer, like a transition buffer, could be thought of as a model. Here, the way that this is actually described is as long as your model is anything where you could say, from this state in action, produce for me a possible next state and reward. If you can do that with your buffer, then it's a valid model. Do you have to do D? I'm sorry, I don't see what you mean by D. Did you say D?
Yeah. You got A, B, C. You have to do update D.
Oh, I'm sorry, it's actually labeled here. Yeah, do you have to use the actual experience in the real world? You know, in the offline setting, we just had the model and we just trained only in the model. Here, there are definitely variants of planning online where you just learn the model. So you use real data to learn the model, and then you plan in that model, but you never use real experience. So yeah, you're right, you do not have to use D. My personal experience is it's useful to actually use the real experience, so that's usually what I advocate for. There is sort of an important question here that you might have inconsistent data. You know, your model might produce different things than you see in the real world, and is it even valid to mix these two things? But we're not going to talk about that. Anything else? Okay, so Here we still have this agent interacting online, and we are really just adding this learn a model step and do a bunch of planning updates. We're going to do these end planning updates in the background. And you might ask, how much better are we actually doing? We're going to go through the whole effort of learning a model and actually having to use computation to do planning with this model. Okay, so it's sort of fun just to think a little bit about how much better we can do if we try to learn these models rather than being perfectly model-free. Okay, so this cute little demo. I'm just going to show you what this looks like. So let's imagine you have this agent in a grid world. It has a start state here at the bottom corner here, and it's going to a goal state up here. And it wandered around the world for quite some time, receiving 0 rewards, and it only gets a reward of +1 when it reaches this goal. Okay, so all along here, it wasn't making any updates as Q values are initialized to 0, and then it got a +1 here and actually does a Q value update there. Okay, so after it's done this very first episode, all of its Q values are 0 everywhere except for right here, and that's all it has learned from the first episode. But clearly, the agent actually knows a lot more about the dynamics of this world after wandering around the world for so long. In fact, it has a pretty good model of how the world works in all these yellow places that it has visited. You know, it knows when it takes the right action, that it transitions to this other state. So presumably, it should be able to use that knowledge. And so here's really what the model is going to do. The agent could actually, after its very first episode, transitions back to the start state, and here it can sit and just imagine to itself, what are action values according to what my model would say? So it's going to do a bunch of planning updates in the background and slowly build up what it thinks are its new action values using only that simulated experience. Okay, so here just to be clear, it's only been at the start state this whole time and just imagining for itself a bunch of simulated experience. Okay, and now after sitting there and using all that simulated experience, it can start its second episode and essentially already has the optimal policy. Okay, so maybe it's sort of obvious that having a model should help, but I hope this example sort of drives home that the agent actually learns a lot about the world when it interacts, and in sparse reward settings, if we don't store that information in some way, we're really not taking as much advantage as we could. Now, Dyna is actually going to look a little different than this. Usually in Dyna, we don't go to the start state and then plan a bunch in the background and get the optimal policy. That's sort of the offline strategy I mentioned before. Really what we're usually going to do is interleave planning and learning. Okay, planning and acting. So here, for example, let's imagine we've taken these 100 steps, and we've taken 185 actions, and we've done 100 planning steps. And now what's really going to happen is the agent will take a few steps. It'll do, let's say 100 planning updates in the background, then it'll take another action, it'll do 100 planning updates in the background, and it's going to be constantly revising its action values both with the simulated experience and with the experience in the real world. So it's really just learning these faster rather than sitting there computing a bunch to get the best action values. We'll let this finish off. Okay, good. So really the key takeaway here is that you can think of Dyna like background planning. Okay, so given unlimited samples, we can or unlimited computation, we can imagine this first agent that just sat in that state after it saw the first episode, and it just went ahead and solved for the action values according to its current model. So it went and solved that Bellman equation. Okay, you can imagine looping over all states, and if we had all this computation, we're essentially doing dynamic programming. Okay, and in practice, of course, we're not actually going to have unlimited computation. We're going to have limited computation, and then really we're thinking of Dyna as this background planning process, where on every step, your agent probably has a little bit of extra computation, and you can use that extra computation to do as many of these planning updates as you can. Okay, so this background planning is sort of a step towards doing these full dynamic programming updates. We can see how useful the full dynamic programming updates could be, and then hopefully some interim number of planning updates are just going to get us to our action values faster. And depending on your application, you can either use more or less planning updates. Okay, so this is really some of the advantages of using this type of strategy. There's just anytime planning. Whenever you have some steps, you might have more computation. Some steps, you might have less computation. But you can always fill it in with some number of planning updates. Okay, and this contrasts something like decision time planning. You heard about Monte Carlo tree search earlier. There's other type of planning strategy called model predictive control that are more about on this time step, I'm going to do a bunch of rollouts from here to decide what to do. That means that the agent actually has to wait for those rollouts to complete. Here for this, it's just saying I have a current policy. I'm going to do whatever my policy currently thinks is best. And then in the background, whenever I can, I'm going to try my best to improve it faster. Okay, of course, you can also take advantage of parallelism. You can do many updates in the background. You can also even do things like partial models. Maybe you only know a little bit about some parts of the world, so you'll only query your model about those parts of the world. And I'll mention a little bit about how we can also use temporal abstraction. Okay, so mostly this slide's a little early, but I put it here anyway because I know later you might look at these slides and you can kind of think to yourself what the advantages are. Okay, so let's think about some specific instances of Dyna. Okay. So in order to actually take Dyna and implement it for your system, you're going to have to make two important choices. You're going to have to decide what is my model and how am I going to do search control. Okay, so here when you're thinking about the model, you're going to remember that the things that matter for your model is how are you going to update your model with new data and how are you going to query your model. Okay, and the only other things that change are the search control strategy. So here, how am I going to decide what states and actions I should ask my model about? Okay, so clearly we should be able to do something smarter than randomly previously observed states and actions. Okay, so that's actually pretty simple. Conceptually, you just need to think about those two things. And then everything else in your Dyna algorithm is going to stay the same regardless of your situation. So let's look at a really simple example of Dyna and then answer the question, what is the model for this setting and what is the search control that this is using? Okay, and this simple example is this thing called experience replay. So first I'm going to get you to think about why experience replay is an instance of Dyna. Okay, so yeah, sure, go ahead.
So do we do like the simulation after one step, or do we have to finish one episode, then we do the simulation? Because if you take one step and you sample from that one step, then you haven't seen anything, just doing the same step again and again and again.
Okay, so you're saying is that can I use my model before I have learned anything about the world and my model is essentially empty? I think, is that what you're saying? Right, so in the example that I showed you, so the question I believe was, what do you do when your model is, you don't know enough about the world, and you would just be simulating all the time from the same state and action? Yeah, so you're right, in the example that I showed you, we let the agent complete its first episode, so it had gathered a reasonable knowledge about the world, and then started actually using its model for planning afterwards. This is an important choice. I don't disagree with this. I don't have an answer for you. You could start using your model as soon as you think it could be useful. And the question of when is a model helpful and when is it harmful is an open research question. There's definitely work out there that tries to say the model is uncertain about this or I don't know enough here, so let's not simulate from this part of the world yet. If you use an algorithm like that, then you just wouldn't use your model for a while. There's another question here.
You just answered my question, so I was wondering how much work there is in building models that know about what they know and don't know, like in the Bayesian, and then use that to change slightly the schema.
So there's definitely some work. There's a lot of theoretical work using models for exploration, and in the exploration work, they want to make sure they have guarantees about their agents. So there they do things like the model is confident in this area and the model is not confident in this area, and they use that information to do a good job of finding the optimal policy. So I would say that there is a lot of work, but a lot of the theoretical work in RL with models for exploration is sort of theoretical. The algorithms are not yet that practical. There is then other people who are trying to think about how could I take my model and recognize that these transitions are wrong and then not use those wrong transitions in some way. That's a much smaller group. I would count myself as part of that group. Aaron Talvedi is doing things like that as well. And there's a few people from Google Brain that are doing it as well. Anyone? Is that a question? Yep.
I'm sorry, this question probably has, but I didn't quite understand the one before with the pseudocode.
Yep.
Why do you have to first do a DD update before you do it in the model when you loop over the model? Does that give you any benefits?
So the question is a repeat of what was asked before, but it's an important question. The question is, really, should we do D? What's the purpose of doing D? I feel like there's an intuition here that it's a bad idea to do D. So do you have a reason why you wouldn't do D? Like, you have this sample. Why not just use it? Or there's someone else who asked the question. Maybe they have a reason they think it's a bad idea. I think you asked it.
I just wondered if it was necessary because I was wondering how much of the knowledge expressed by the update D could be rolled into your model, or if there are constraints on what we're calling a model.
Right. I mean, again, the answer is a little bit that this step is maybe not that important in the sense that here you have n planning updates and here you just have one update. So you would think that this would dominate. Sometimes in practice, people will do things like They will always use these model-free, they'll use experience from the real world to do updates, and then as time passes, they start using the model less and less, because no matter what we do, our models are wrong. So there is this sort of well-understood property that in early learning, the model should help, and as time passes, your bias is going to start meaning you can't converge to its optimal solution, so you want to start using the model less. I'm not sure I really believe that that's exactly true, but it's a reasonable intuition. So then D would become more and more important.
In general, is the model parametric or non-parametric?
You can use both. I haven't told you yet what your model can be. You can use your favorite strategy.
So that might have been answered previously, but do you evaluate the output of your simulation? So for example, to contextualize it, when humans dream, we have some implausible sample that is generated. You know that's not realistic, and you don't usually act on that. Does that happen in models?
So this is sort of what Joshua asked a little bit. Is there some understanding of or quantifying when the model is uncertain or wrong in some way? It is definitely an important area of research, not really that well understood. You are definitely right that the way I have written this sort of generic algorithm is trusting the model perfectly, which is, you can imagine adding in lines here that say, if model not sure, throw away sample. Like there might need to be some additions to this very generic algorithm. At the back. Does the model hurt exploration?
Yeah, by using a model, does it hurt exploration?
Okay, well, I mean, exploration is a difficult topic. So if you use your model wrong, I'm sure you could use your model to hurt exploration. But a lot of really great exploration algorithms are based on having the model. So in general, having a model could really help you a lot in exploration. For example, you could use your model to say, I haven't seen this thing in a very long time, and you could actually do planning updates to go revisit parts of your space. Or you might have seen one really interesting reward once, and your planning updates would really help you back that up and go see those things again. So in general, I'd say the model should help us in exploration. Using models in a bad way is not good. I'm imagining what you're thinking is we have optimism, and then the model updates constantly in one region, and then it removes all that optimism, and we'll never actually go explore that area. Sure, we want to try to not do things like that. Okay, I'm going to keep going. So let's think about one example of this. You're already kind of jumping ahead to all the questions that you really want to know about how you use Dyna. I'm kind of going through this slowly, but that's okay. We'll just revisit those questions. Okay, let's think about one very simple instance of Dyna. I like to think of this as the simplest instance of Dyna. Okay, so we're just going to use experience replay. What this means is as we're interacting with the world, we're just going to store all of our data into a transition buffer. Let's imagine you have a sliding window. So maybe you don't store all the data you've ever seen, but you store a largish buffer of the most recent data you have seen. Okay, and then we're just going to sample mini batch updates from this buffer, and we're going to update our value function or our policy. Okay, so you can kind of think of this like a batch strategy or a sliding window batch strategy in the online setting. Okay, you can think of it that way, but you can also think of it like Dyna. So I'm going to ask you guys the question, how can we think of ER as an instance of Dyna? And what that really means is, what is the model and what is the search control? And just to make this a bit more concrete, I have taken the DynaQ pseudocode, I have removed parts and kind of told you what the ER algorithm would look like. So here you're going to have a buffer, B, and now we're going to add some, I don't know why I added just S and A. What I really meant is add the entire transition to the buffer B here, so S, A, S prime, and R. Drop the oldest sample. We're going to grab a random sample from the buffer B, and we're going to do our Q-learning update here. Okay, and I told you that usually we grab a mini batch, but for now let's just imagine our mini batch is of size 1, so we're just going to grab one sample at a time. Okay, so, let's go here. Okay, so I'm actually going to make you think about this. It shouldn't be too hard of a question, but I'm not suggesting it's a trivial question either. So do think for yourself, what is the model here and what is search control? I'm going to give everyone a chance to think about it for 20 seconds, and then I'll get someone to answer and show you. I see a question back there. Is it an answer to this question or is it a question? Okay, sure. I'll say it's been 20 seconds. Go ahead.
Is it the original underlying model from which we are seeing the states and actions?
Okay, so you're saying here the model for ER is the true model of the environment. Okay, and then what's the search control? Okay, that's fun. Anyone else have any other answers?
Is the model the buffer
Okay.
and the search control is random?
Yep, good answer. So I'm going to just sort of show you what that looks like in this Dyna diagram. So remember in Dyna, we had this step of model learning, and then from this model, we would ask, given a state and action, tell me what a next state and reward could be. Okay, so here you can think of our model learning as what sort of someone asked up there. It's a non-parametric model. We're not actually going to learn any kind of parametric model like a neural network or something like that. We're just going to store our data, and we're going to say our data is the model. Okay, so you can think of this like a non-parametric model. Okay, so our buffer really is the model because it tells us something about how the world behaves. And then when we do search control is just going to say, is this going to show up? It's just going to say, take a random state and action in my buffer. That's the only states and actions that I know anything about, that my model allows me to know anything about. And then the next reward and state that it's going to produce is exactly the state and reward that I saw. Make sense? Okay, good. So non-parametric model, it's a pretty limited non-parametric model. And you just take the data that you actually saw as your sample. Go ahead. Yep. You got it. Yeah. I literally just meant the oldest sample. We're going to use the most naive sliding window buffer. So 100 times, if your buffer's of size 100, you drop whatever you saw 100 time steps ago, which is the state and action, next state and reward that you saw 100 time steps ago.
So this actually will hurt exploration.
Sorry, say that again?
Doing that actually will hurt exploration.
Will hurt exploration. Why do you say that?
Well, I mean, so if something you have for a very long time haven't experienced that before, and then in the recent time you didn't experience that, you simply just drop that out, right? So I thought when you say that, I thought you are meaning I drop the oldest sample at the same state, taking the same action.
Okay. So I think the point is that this strategy, which is a very naive strategy to use Dyna, could harm exploration. Here I think you're imagining a better strategy that would be even better for exploration. I'm not sure it would harm exploration much more than just a regular model-free online updating approach. But again, maybe you're imagining that the most recent things get updated more and more, and then that's somehow influencing how you're going to explore other parts of the world. It's not immediately obvious to me that it would harm exploration. It's definitely not a good exploration strategy. If you're just relying on doing updates to your Q values using a buffer of size 100 and with no other exploration strategy, that is likely going to fail in many cases. So we definitely have to think about exploration. But actually, I'm sort of separating model-based RL and exploration right now. I'm just thinking about if someone handed you a model, how could you do things that we think of like planning in an online way? And then, of course, we should try to use our model to do good exploration too. But yeah, not talking about that right now. Okay, right. Okay, so why did I make you think about how experience replay is an instance of Dyna? One of the reasons is just that right now a lot of the successes we have in RL are using experience replay. And I like to think of it as the reason that it has been so successful is because Dyna is something that we should be using in our algorithms. We should be, as much as possible, learning a model of our world and extracting as much information as we can from our samples. So if experience replay is very successful, in general, we should actually be able to do something smarter than this sliding window buffer as a model, and we should be able to do smarter search control than just essentially randomly sampling from our buffer or maybe using some priorities on our samples. Okay, it's pretty intuitive that we should be able to do better than that. So it's sort of a hopeful, it's both because you've probably heard of experience replay, so it's kind of nice to see how it's connected to Dyna, and it's a hopeful story for how much more we could actually do if we do this in an even smarter way. Okay, so you can imagine, for example, some advantages of a learn model over a transition buffer are things like compactness. Right now, we keep a sliding window buffer by dropping some of the oldest things, or maybe some smarter strategy, but generally some variant of that, because we just can't keep all of our data. That's not a realistic strategy. So something like a model is actually, in some sense, implicitly keeping all your data, because it's just compactly storing that information. Similarly, a model is actually going to let you get coverage of the whole environment, which a sliding window cannot. And maybe the most fun thing is that we can actually query our model from different states and actions. It's really hard to do search control with something like a buffer. Okay, so now let's jump into the questions of, we just saw the most basic strategy to do model-based RL, which is experience replay. Now let's think a little bit about what are other things we could do to pick the model and to do search control. And I'm still not exactly going to answer the question of what are the best models to do, but I'm going to get you to think about the types of models we could care about. Okay, so we started off with, what are the possible models that we could learn? And I said, the most obvious answer is let's just go ahead and try to get the transition dynamics, p hat. Okay, but I have this arrow here because I'm clearly going to start telling you that we could maybe learn simpler models. I'm going to say that this is the most complex model you could learn. Yeah, let's go with that for now anyway. We could also imagine something like a transition model that's not trying to be on the states or the observations that we actually see, but it's going to be a transition model on the agent state. So you just saw the POMDP lecture about, imagine you're in a partially observable world, and you're going to try to construct state. Okay, agent state I think is a very important thing. What we're probably going to be doing is building models from agent state to agent state. We'll talk about this a bit more. You might even go a little, so that's still trying to learn transition dynamics. You might instead just do something even simpler. What if your agent already had a bunch of predictions about what are the outcomes of future observations or features that you might see in your world? You would hope, that tells you a lot about how your world works. You'd hope to be able to use that somehow in your model-based RL strategy. You might even make something even simpler. Maybe you don't know what happens about specific observations. Maybe you just know about rewards or cumulative rewards. And now we're sort of starting to see that there's all these really basic predictions we could make about the world. And we could sort of think of them like models and ask, could we use these as models to improve our RL agents? So this is maybe a little philosophical, but I just wanted to tackle this philosophical point for a reason. You could even sort of think of Q of SA as a model. It's telling you a lot about what could happen in this world if you were to, it would tell you a lot about what's going to happen in the future, what rewards you might see if you were to follow a certain policy. And then, when you start having these philosophical questions about what is a model, you start asking questions like this that I don't think is a particularly helpful question. Go ahead.
So QSA is dependent on the policy, whereas the transition operator is not, right?
That's very true, yeah. So that's why I want to say that this is clearly not true. SARSA is clearly not a model-based algorithm. We should never even say things like this out loud, even though that does happen sometimes. So what I really want to say is, what do we really mean by a model when we say model-based RL? And then that can help us answer the question, what kinds of learned models should we consider? And here I'm proposing that when we say model, what we really mean is the agent has some predictions about the world, so we're going to call that the model, that allow it to improve the estimates of the optimal value function or policy, and it allows you to learn about new things faster. So for example, if now you'd like to learn about a new option, you guys have not yet learned about options or skills. Andre Breda is going to tell you about that. But you might also want to ask about little subtask policies, like how do I get to the door? Things like that. Then, it's pretty clear now that QSA is not a model. This is still a slightly imprecise definition, but if we start thinking about what we want our models to do, we want our agent to build up understanding of how the world works so that it can improve how much reward it can receive in the real world, and so it can learn about new things that it wants to learn about the world faster. Those are sort of the two criteria we'd like to have. So what that also means, though, is that our model doesn't have to be the transition dynamics. We can sort of try to understand a broader scope of different models that would be useful for planning, that are in between full transition dynamics and something as simple as QSA. Okay. Good. So sort of with that in mind, let's think about what are some important aspects we should think of when we're doing model learning. And the first one I'm going to mention is the state-to-state versus observation-observation. Go ahead. Okay, so I think the question was, I had made this sort of comment here that I had not actually talked at all about, which is that a model could help you in non-stationary problems. And your question, I think, is, it's not clear how a model could help you in non-stationary problems. Maybe especially because the model would also be prone to being incorrect due to non-stationary. Maybe maybe you're not, we weren't saying that. There's this very basic proposal right now that's called Dyna Q+, where you could have your model does sort of know what the transitions look like. And you could say, I'm going to keep track of what parts of the world I haven't visited in a while. I'm going to add bonuses to those parts of the world as reward bonuses to my real reward, and that's going to sort of encourage the agent to go revisit parts of the world it hasn't seen in a very long time. So it's a way to sort of get your model to tell you to go, you can use your model to plan to get to parts of the world you haven't seen in a while. But you can imagine other things that your model could help with non-stationary. You can imagine your model sort of knows how the transitions work, but that your rewards actually change sometimes. Let's say you deplete some resource over here, your rewards decrease for that part of the world. You could actually plan more quickly to go see some other part of the world where you had a secondary reasonable reward that wasn't as good as this reward. So non-stationary and reward, I think, would be another way models could help. Does that answer your question? Okay. Okay, let's continue. Okay, so I'm going to sort of have a list here of things that we should pay attention to when we're making our learned models. I'm going to start with this comment about state-to-state versus observation-to-observation. Okay, so right now I just said we're going to imagine that we're going to learn transition dynamics on whatever is given to the agent. We're going to say for state and action, give me the distribution of our next states and rewards. That's probably not really going to happen in practice. In practice, your agent's going to take either input observations that are much too complex and try to reduce them down into something smaller that only reflects the relevant information it needs, or it's going to be in a partially observable environment where it actually needs to build up agent state. It's not going to be able to learn models from previous observation to next observation because that will be insufficient. So in general, when we start thinking about Dyna in realistic settings, we're going to want to construct models on agent state. So that means we're going to imagine our agent constructs some agent state, and then we're going to have to, on top of that, learn a model that goes from agent state to agent state. Okay, this seems like a pretty minor point, but I actually think it's really important. So I'm just going to dwell for one moment. One thing that's commonly done right now is things like observation-to-observation models or image-to-image models. You could argue that that's a bit overkill. Does the agent really need to know, given this image, what is the precise next image that is produced? It's probably a lot more reasonable to say the agent is going to take this image, bring it down into a feature vector that it thinks are the most important things to know right now to do a good job of prediction or of acting. And really, we only need to do planning inside this state space that the agent has decided for itself is important. I feel like I saw a hand somewhere, though. Yeah, go ahead.
So when we replay the state,
Mm-hmm.
does it have to be a previously encountered state, real state?
Okay, so now you're asking about search control. So I think the question was, when we replay the state, did you say replay? When you replay the state, does it have to be a previous state and action that you saw? Definitely not. But let's talk about the model for a moment first, and then we can get to search control. And then I'll get you guys to tell me some suggestions about search control. Up there.
If you do have already transition dynamics from your model, can you do dynamic programming instead of Q-planning? I mean, is there any restriction to Q-planning?
Okay, so I think the question was, if you have a transition dynamics model, why would you do Q-learning? Why wouldn't you just do dynamic programming? You could say that Q-learning is an approximation to the dynamic programming update. It is like a value iteration update. It's approximating what the Bellman equation would do. And then Dyna is the way to try to get to do more dynamic programming updates, but within whatever computational budget you have. So in some sense, I guess I'm advocating for, yes, we should do things like dynamic programming. There's definitely model-based algorithms out there that take learned models and then in the background actually go and fully compute the value function for those learned models. So it's definitely not a bad strategy.
Are we learning full transition models or the expected transition models?
That's all I'll tell you on the next slide. Yes. Anything else? Okay. Okay, so maybe this is not so controversial. But I also want to point out that Dyna is not at all restricted to the fully observable case. Whenever we write state, really sometimes we're going to imagine that we're going to replace state with agent state, and it is always up to the agent to, in a partially observable environment, to build up this agent state. Okay? Good. So here, this could have been model-based RL in POM-DPs, not just in fully observable. Okay, another important aspect is to ask expectation versus sample models, which is exactly what you're asking about. So let me just tell you what the difference between these two things are. So in a sample model, this is what we've already been talking about. We imagine someone hands you a state and an action, and your goal as a model is to return a sample of the next state and reward. Okay, and so examples of sample models, if you were to actually try to learn parameterized sample models, could be something like this mixture density network. You might input your state and action. You're going to learn, say, some neural network. You're going to pass it through some neural network, let's say, and what it's going to output is the parameters to some mixture model. Okay, so here you might be mixing across two Gaussians. C1 is the coefficient for the first Gaussian, C2 is the coefficient for the second Gaussian. We had their means and their covariance matrices here. And here the fact that you have to learn this function here that because this mu1, sigma 1, and C1 are all conditioned on the state. Okay, so it's a conditional mixture model because you're saying given this state and action, I'm going to have different means, variances, and coefficients for my Gaussian mixture model here, and that's going to tell me what my distribution, for example, over states is in this case. Okay, so hopefully you've seen mixture models before. The step to conditional mixture models is not so different. It's just that you have to parameterize your means, your variances, and your coefficients. If there's a question about that, do ask. Okay, and of course there's just lots of other types of generative models out there where you just need some strategy that says, for this given input, give me a sample of the thing that I'd like to see. Okay, an expectation model says instead, given an input state and action, what is my expected next state and reward? Okay, here's where I'm going to ask you a question, just to make sure you're all awake. Okay, so imagine you train a feed-forward neural network with input-output pairs, this S and A, and then the output is S prime and R, because you're trying to say, given an SA, give me an S prime and an R, and you use a squared error. Is this, if you were to go ahead and do this from a big batch of data, are you going to get a sample model or an expectation model? And you can just sort of privately answer this to yourself. Okay, does anyone want to say? Actually, wait, I'm going to do the hands thing. Who thinks it's going to give you a sample model? Okay, who thinks it's going to give you an expectation model? Okay, the expectation model. And then everyone else just, didn't want to answer or is sleeping. That's fine too. Okay, so the answer here is that it's going to give you an expectation model. And so if you go back to the things that you learned about in your deep learning session, whenever we have these pairs and we're using a squared error, really what you're trying to do from your neural network is, or whenever you're doing any kind of regression problem this way, you're trying to say, for my given input state and action, I of course can't predict specific states, next states, and rewards that I saw. Those are stochastic. I'm going to learn some statistics, so whenever you use squared error, you're going to learn something like the expected target that you're looking for. So when it's an X and Y pair, you input X and you're predicting expected value of Y. Here we're inputting states and actions, so we're going to learn expected next state and expected reward. Okay, so then that just leads me to examples of expectation models. So if you were interested in an expectation model, you might just do something like learn a linear function of input state and action using a squared error, or you might do something like a standard feed-forward neural network. Okay, so now the question would be, why would you learn a sample model? Why would you learn an expectation model? And maybe for most of you here, learning a sample model makes a lot of sense. Maybe the real question is, why would you learn an expectation model? Let me just start off by agreeing with you. There's definitely some issues with trying to learn an expectation model. So I really like this picture from Cosmo Paduraru's thesis. This is a pretty nice thesis. But here you could imagine if you learn an expectation model, you're in some state that's given by x, y, and then you're going to transition to some next state, x plus 1. Randomly, this x, it always goes to x plus 1, but it could transition to y plus 1, y, or y minus 1. It could transition to y plus 1 or y minus 1 with 50% probability, and then the expected next state is going to be this y here. And you could imagine a situation where, I did this picture backwards. Replace these both here with not so bad, and put war and destruction in the middle. Unless for some reason you're optimizing war and destruction, I guess. So let's either imagine this is correct and you're a bit of a masochist, or I accidentally flip this. So here you might imagine that this expected model, if this was war and destruction, is not at all what you intended, and you're actually going to imagine you're transitioning to this state. Or I guess in the other way around, you might, if you sampled your model and your expected next state says that this is not so bad, then you might actually think that this is not a terrible route to take, but really you're always going to go to some war and destruction. Okay, that's why this image is this way. Okay, and this really just comes down to this very simple rule that you guys have all seen, I'm sure, which is that the expected value of some function of a random variable, when this function is not something simple like a linear function, is not equal to the value of the expected value of the function of the expected value of that random variable. Okay, so here, just to unpack this a little bit more, here if you wanted to know, what do I think is going to be my expected return from here, we're often dealing with expected returns to make decisions. Then we're saying from this state, here's my expected reward plus my expected value in the next state. If instead your model doesn't actually go compute the expected value by simulating a bunch of next states, then instead it's going to give you the expected next state as an output, and you're going to query your value on that expected next state. Okay, and these two things are definitely not necessarily going to be equal. Okay, so trying to use an expected next state might not actually give you accurate estimates of what your return is going to be, and in bad situations it could be something like this. Okay. All right, I guess I could underline those. So those two things are not equal to each other. Okay, but on the flip side, there are things that we would like about having an expectation model. The very first thing is it's just easier to learn. Learning distribution models, we do have some good tools for it, but learning something as simple as a statistic like the mean is just simpler, and simpler is good. Okay, so if we could do it, we would like to learn the simpler thing. Of course, the other thing is that if the world is deterministic, an expectation model really is a sample model because you have deterministic next state and reward. So then, of course, learning an expectation model is not bad. And maybe it's not so unreasonable to sometimes imagine the world as deterministic, is my opinion. Many people would disagree with me on that. Okay, and then the other sort of neat thing is that if the value function is actually linear in our agent state and our model is on agent state, then there's actually no disadvantage to using an expectation model. So you could have used a sample model, but you could also have used an expectation model, and it's going to provide you exactly the same planning updates. So if you want to see that sort of spelled out a little bit more, you can go look at this paper called Planning with Expectation Models. But it's sort of an elegant argument for if we wanted to learn something simple, if we're learning an agent state that already summarizes things that we think are important about the world, again, maybe it's not so unreasonable to imagine that our value function is linear in agent state. Okay, so the point of that part was just to tell you, you could choose expectation models, you could choose sample models. The repercussions of that choice are actually pretty stark. You do have to pay attention to, is it reasonable to learn an expectation model here? I suppose you can always learn a sample model. Okay, I'm going to go over in one more important aspect and then just tell you a few more without actually going over them. But let's think about one more thing, which is in our models we might ask the question, are we going to do rollouts forward with our model? Are we going to iterate our model forward? Or are we going to do something with temporal abstraction? So let me tell you what these things mean again. So let me first tell you what I mean by rollouts. So yes, you saw Monte Carlo tree search earlier, but you could imagine your agent might want to know, not just from the state in action, what is my next state and reward? You might, of course, want to know, okay, and then what would happen after that? And then how about after that? You might actually want to get entire trajectories up to some depth to tell you in a less myopic way what is actually going to happen. Yeah, go ahead.
Do you think sample models are realistic in the sense that we need to have support over all the possible next states, right? So there could be like 10 or 170 states for it.
Oh, I see. Okay, the question was, do I think sample models are realistic? I'm naturally sort of a continuous state kind of person, so I'm imagining for using these parameterized functions, we can deal with these infinite spaces because they're nice continuous spaces, and we're just going to generalize across them. But does that answer your question? I don't think we're going to learn a table of values for each possible next state. Generalization is beautiful. We should definitely take advantage of generalization. But anyway, is it realistic to learn complicated distributions? I don't know. Okay, anyway, so you could imagine taking your model and actually asking what are some multiple step outcomes from this state, and you could hopefully usefully use that information. Actually, there's this nice paper out there that says if you have a model, it can be really helpful to do longer rollouts rather than just many short ones, because it lets you sort of get to these parts of the space that you don't know much about. It's sort of helping with the exploration problem. But at the same time, there are some issues with rollouts. So I really enjoy this really nice paper from Aaron Talvity. And this paper is showing that if you were to try to do rollouts by just taking a model and introducing a particular limitation into it that is not that stringent of a limitation, rollouts can really suffer catastrophically. So here's what this top line here is showing you what does an actual sequence of outcomes look like in this real world. So you have this little agent on the bottom, it's shooting at these blocks, and it's transitioning in this way. Now, if you were to take this exact same input state and start using your model to iterate forward what it thinks are possible next states, the rollout errors accumulate and it starts to produce these really weird looking images that you would absolutely never see. Okay, so I almost didn't even have to show you this. It's sort of intuitive that iterating our models forward can have this compounding error problem. And if we really want to ask questions about long-term behavior, rollouts is likely not the right strategy. We can hopefully roll out some number of steps, but it's, I think, unrealistic to imagine we can roll out to a large horizon into the future. So the other thing we're probably going to want to think about when we're learning our models is to do some kind of form of temporal abstraction. So options keep coming up. You still haven't learned about what an option is. Again, you're going to learn about that tomorrow. But what we're really going to want to do is have things like macro actions. So here you might imagine that, let's imagine you have a navigation robot. It could have a policy that tells it how to get to the door. So instead of needing to know about specific actions in a sequence that it's going to plan around, it might just already have some option, or I'm going to call it a macro action, that says, take the action that is go to the door. Okay? And that action is composed of many smaller actions. Okay, and now the agent can plan over these options instead and treat them sort of like actions. It can ask the question, from this state, if I were to take this option or macro action, then what is the outcome state that I will get to when I'm done taking this option? And what is the reward that I accumulated along the way? Okay, so we're still sort of imagining we have these simple transition models where all we've done is sort of change the actions that we reason about to make it these longer temporal abstract actions. But the algorithm doesn't necessarily have to change very much. So one nice advantage of thinking about models this way is that we can now reason about longer horizons, multiple steps into the future without actually having to do these long rollouts. Okay, brief introduction options. Okay, and in general, there's other things you might actually think about for your model. So I've talked about these three, but there's lots of other things you might ask. Maybe you don't want to learn full transition dynamics. Maybe you just want to have some subset of predictions about the future. You know, what does that model look like? How could you use such a model? You might want to think about, does your model actually output certainty estimates, so that you could actually use that information to choose to use transitions. And I think these two things are really important. One is how efficiently can you actually learn your model? If you're going to be interacting in the world and it takes a really, really long time to learn your model, but your goal is to learn a model to learn your value function faster, this might be a bit of a problem. So we really have to ask the question, can I learn my model fast enough for it to be useful? And we're also going to be using our model for planning in the background, so we also have to ask the question, how computationally efficient is it to sample it? I'm going to give you guys a chance to wake up for a second and see if you have any other suggestions. Are there any other things that you think are important to think about if you're going to use Dyna and going to have a learned model? Up there. Sorry, the one thing that might be important is the type of model, like the order of the model? So for some reason, I don't understand what you mean by order. Do you mean like order not as in ordering of things, but like order like the scale or? Okay. Gotcha. Okay, so you're saying if you had some kind of parametric form, what might matter is the complexity of the actual features, like if you're using higher order polynomials or lower order polynomials. And then maybe you also mean the power of the model, then, like how well can it actually model some complex nonlinear functions rather than simple functions. Yeah, so definitely the parametric form, which you're right is not listed up here, is very important.
How about generalization? If you are using training data, then the model might just overfit on these observed examples and just try to interpolate or stuff like these. But how do you make sure you can generalize to the unseen situations?
Great point. So the other suggestion was the way that your model generalizes probably matters a lot. Really good point, actually. That should definitely be up here. You said it one direction, so the suggestion was you want to make sure that your model learns on some parts of the world and then it actually generalizes well to other parts so you can exploit that generalization. I would also argue the other way around. You want to make sure that your model doesn't overgeneralize in some way so that you're making these wrong inferences. In fact, I would say a lot of model building strategies, especially for exploration, have been sort of conservative and have preferred local models that say, I really only know something about this part of the world and I'm going to exploit that as much as I possibly can. But you're right, the way that it generalizes is very important.
Maybe explore, the model should know how to explore so it knows what else it needs to
Okay, that's a good point. So the model should maybe know what it knows so that it can help you guide your exploration, to gather data to learn the model better. Interesting suggestion.
If the model is generated from an environment with a partial observability, like some unobserved context in FPR file we use in different context, it might carry some bias along with it.
Okay, so the bias that your model might have in a partially observable environment. Okay, and trying to be robust to that in some way. Being robust to your model biases, I guess, a good point. Understanding your model biases is maybe what should be on here. I'll do one more.
What do you think about like learning factored models? When I say factored is that your transitions are given your condition and actions are independent, certain aspects of the state space.
I think learning factored models is a great idea. I think that was the question. What do I think of learning factored models? Okay. There's only so much more time left. So let's go to the second thing now. Okay, so we talked a lot about models. I still haven't told you anything about specific models. I just sort of said when you go and start using model-based RL, these are sort of some of the model choices you should keep in mind. State to state, are you going to use temporal abstraction? What was the other one I said? Expectation versus sample models, maybe one of the most important ones. So, keeping some of these things in mind doesn't tell you what model to use, but it tells you something about how you should go about and thinking about what model to use. Okay, let's talk about search control, which I think is actually an under-thought about but extremely important part of Dyna. Okay, so let me remind you what search control is. It's really just saying what states and actions should I pick so that I can ask my model about what the outcomes from that state and action are. Okay, as always, let me tell you about a bit of the things that people do right now, and then I'll do the fun thing of asking you guys your suggestions. Okay, so some natural thoughts about how you might do search control. So random is where we started. That's not a very interesting strategy. What we'd really like to do is say, I want to pick a state and action that's going to make me learn the most. It's going to make me either identify that there's a part of the world that I should visit, or it's going to improve my value, my policy a lot. Okay, so one natural thing to do is then prioritize samples with higher error. So if there's some part of the world where you predicted something was going to happen, you thought you were going to see a reward of 0, but you suddenly saw a reward of 1, then there's a lot of learning that can happen there. So you're going to take the fact that you had high error there, and you're going to prioritize simulating experience from that state and action so you can learn more about that part of the world. Okay, so here, the way that you would actually operationalize this is you could store the observed state and action that you have and store with it the TD error that you saw, and then things that have high TD error you're going to prioritize when you do your search control, and you're going to ask your model about those. Hopefully that's clear. Okay, another thing that you might do is you might say, I just saw some really important state, and I'm going to update backwards from these really important states. So here, important might actually be something like prioritize states. I just saw a state, it had really high error. I'm now going to update backwards from this state. Okay, this is maybe a little less obvious why this is a good idea, so I'm going to get you to think through it with this very simple example. Okay, so let's imagine this really simple grid world. The agent starts in a state over here. It has a goal state over here. And everywhere in this world has a reward of 0 except for at the goal state where it gets a +1. Okay, let's just imagine it initializes all of its Q values, action values to 0. And whenever it's wandering around this world in the very first episode, all of its updates are going to be 0. Okay, because it predicts that it should see a reward of 0, and it does see a reward of 0. So it predicts it's going to see a return of 0. Its target is going to be 0, so it's never going to do any updates. Okay, so let's imagine just wandering around learning nothing, and then it's going to reach this goal state, and then it's going to transition back to this start state. Okay, so I want you to think about the answers to these two questions. What if the agent updates around the start state after it transitions from that first episode, and what would happen if the agent updates around this goal state? So very first for this one, what happens after this first episode when the agent updates around the start state? Using the planning update. So when I mean update, I mean it's going to do a bunch of planning updates in the background. It's going to update a bunch of states here. What do you think is going to happen? Sure, go ahead.
Nothing, because all the went around is 0.
Right, exactly. So it has transitioned back to the start state. It still has predicted values of 0 there. It's really only updated its Q value here to say I know there's a reward of +1. So it's still completely wasting its time doing planning updates around the place that it is right now, the start state. Now, if it did updates from predecessors around the goal, that means it would do updates for these states that are directly beside the goal. What's going to happen then? Sure, go ahead.
You're going to be able to usefully propagate that reward signal backwards. So instead of having 0s all over the place,
Good, so the answer was we're going to be able to propagate that information backwards. So here I updated some Q values near this goal state and now think that my values are a little bit higher. My TD error is no longer going to be 0, and then I'm going to generate a predecessor from this state, and then I get to start kind of bringing that value backwards. Okay, so you sort of saw how eligibility traces can spread value back by actually doing predecessor updates from a state where you just did lots of learning. It's sort of spreading back all that learning as well. Okay. Good. So I would say that those are two maybe the most important ways that people do search control right now. Another really sort of natural strategy that is not maybe as important is you could also think about updating with on-policy transitions. So you might still, rather than randomly picking states and actions, you might still randomly pick an observed state that you saw, and then you could actually ask what would be the outcome for the policy that I currently have right now. So you're sort of directing your search control to give you more information about what you are currently doing. Sort of a natural idea as well. So if you want to know a little bit more about, what are the properties of these different search control strategies, this paper sort of goes through and tries to do experiments saying how much does it help to prioritize, how much does it help to have predecessors, and how much does it help to do on-policy updating. And really the conclusions from this are that generating predecessors is a really great strategy for search control, and it's an important strategy if you actually want to beat something as simple as random sampling. So if you were to do something like experience replay, or you were to go to the full effort of learning a model, you're going to get no benefits over experience replay unless you do something smart with search control. And that something smart is something like using predecessor states. Okay, so it's sort of a surprising result. You would think learning a model would mean you should do better than something as simple as having a buffer. But without smart search control, it's not worthwhile. Okay, I'll mention one other search control strategy that has been used, which is just to focus updating on the current state, or in a region that's around the current state. So this is sort of an intuitive idea. It's also saying, I'm in this state right now. I'm going to focus a bunch of my planning updates on states I'm going to see very soon because I want their values to be as accurate as possible so that I can make the best decisions possible. So this is sort of incorporated in this idea in Dyna too. It's also in this other paper about search control that's recent. And there's a different paper that sort of learned local linear models to try to update states as much as possible that were nearby states. Okay, but I'm going to conclude that with, these are 4 strategies that I have seen for search control. I really believe search control is extremely important to get model-based RL to be worthwhile. And we don't actually have a lot of great suggestions for search control. So again, I'm going to ask you guys for fun, do you have any other strategies you think would be good for search control? Yeah, you get to go again.
Can we keep a frequency of the number of times a state is visited
Okay, so you're going to imagine storing somehow counts or some function approximator that tells you something about counts that says this state has been, I haven't seen it very much, so I'm going to simulate more data from that state. That's an interesting suggestion. We'll do one more, yeah.
What about using some sort of GAN network, the adversarial, using one as a choose point, using the other one to judge if this point as we explore it is good or not, and then
Okay, that's an interesting suggestion. So what you're saying is that there would sort of be this strategy of generating something that would, generating a state in action that would cause the most learning, or like the agent would get most wrong somehow. And so those would be useful states and actions to use. Yeah, that's an interesting suggestion. Okay, we'll do one more.
Can we learn a generative recurrent model that can predict through time the reward directly by observing the state where there is no reward and the reward signal is very sparse?
Okay.
Use this generative model as a reward.
I didn't exactly get the suggestion, but I think the suggestion was, could we learn a model that says from a given state, predict outcomes that are further into the future in sparse reward settings?
Yes, so when you don't have a reward and your reward signal is very sparse, you train the model to predict this reward. What would this reward be in the current?
Okay. And then you would use that for search control by saying this state has high reward.
You get a reward and you train this model, you train this predictive model or a generative model, and when you don't have anything, you use the output of this function as a reward.
Okay. I think that might be more of a reward-bonus strategy, but we'll talk about that later. I will answer one more question or give one more suggestion, then we'll keep going.
do you think if you learn a model in a 3D fashion, this voxel space or something like that, then you can just see the goal and walk towards it, whereas in 2D we can't really, like if I were a 2D object, I couldn't just properly get to my
things occluded or something.
Okay, so you're saying we should.
Change the way the search algorithms itself made because the dynamics is different.
I think what you're saying is, shouldn't we make our environments easier so that our agents can learn more easily? I think if you can design your environment so that your agent can learn faster, that's great. I'm not sure if it's perfectly relevant to this, but tell me more about it afterwards, because I'm interested in the suggestion. But I'm going to keep going so that we can get to the last part, which is going to be very short anyway, and to make sure that I finish on time. Okay, I just wanted to sort of leave with this section on part 2. This is the very end of part 2, where I want to kind of ask, so are we done? A very natural thought could be, as long as we can learn a very accurate model, say with deep neural networks, we have all these beautiful modeling tools now. We should be able to learn accurate models. With Dyna, are we going to be able to actually get really sample efficient agents? And sort of what I wanted to do going through these 2 steps in Dyna is to say no, we do not have that yet. We are not done, and really mainly for 2 reasons. I think we have a big question about how we should do search control well so that we can effectively do planning in the background. Like I mentioned right now, there's also examples of situations where you could do a bunch of planning in the background, but it was essentially a complete waste of time because you didn't pay attention to how you're doing planning in the background, so you're not really gaining anything over model free, and we're going to continue being sample inefficient. So better understanding the search control question, I think, means we are not done. And one thing I didn't yet say, but I'm just going to show you an example, is that small errors in the model can result in big errors in the policy. And so model-based hasn't just taken off as much as it could have, because I think partially because of examples like this. So I'm going to give credit to Tahir here. He made these nice pictures around a bunch of experiments. But let me just give you a really simple example of a situation where you would think it should be easy to learn a model, but just like a small thing that you wouldn't have anticipated can cause failure. So again, I just took this little simple grid world, but here now I'm going to imagine the agent knows that there's states here, but doesn't know that those states are unreachable. So you can imagine it has parameterization from 0 to 1 and from 0 to 1 here in an XY space. It initializes its value functions optimistically. Let's say it initializes them to 1, because it can only ever get a reward of 1 here. And then it wanders around in the world for quite some time, and slowly its values are going to start being pushed down away from 1. Okay, and then let's imagine it is in this state, and actually its model knows that when I take the up action, I usually transition to a state that goes up from here. Okay, in this case, in this corner of the wall, it may be a little bit inaccurate. It actually can't go into that part of the wall. It should stay in that state. So there's just a little bit of model inaccuracy. But your value for this state, because you've never updated it, is still whatever your optimistic value was. Okay, so what your agent is going to think is that in this state, if I take the up action, I'm going to enter this state that has really high value, because that's what my value function tells me. It tells me that it has high value in this state. You're going to bootstrap off of this, and you're going to increase the value for taking the up action here. And then if you do a bunch of planning updates, you're going to just start increasing the value for this wrong action, and your agent's going to get stuck in this corner, constantly thinking it can reach this unreachable value. Okay? And here you might say this is maybe a little bit unlikely. Your model should learn not to go perfectly up. It should learn that in this corner it can't go through this wall, but even just a little bit of inaccuracy, thinking it can go just a little bit into the wall, means it might accidentally see these high values. Okay, so these sort of small errors in the model can be super magnified if our values are wrong and our agent suddenly changes the way that it's going to behave. So I just wanted to end off there saying model-based RL is really promising. It's something we all really need to work on, but we still have to be a little bit careful about just using it out of the box. There's more questions to answer. Okay, now let me just finish in the last minute that I have, just to give you a brief discussion about other ways you could use the model. I gave you this one strategy. I went in depth because I think understanding the fundamentals for one idea is usually more helpful than understanding a big breadth of things. But there are still lots of other ways models are used, so I just kind of want you to know about some of them. Okay, so this slide title sort of summarizes this. Models are really useful, and because they're really useful, they've been used in a lot of different ways, not even just for planning like we talked about. So there has been all these other really great algorithms that I like that are very related to Dyna. They are also going to go and learn a model from experience, but then instead of doing the sort of interleaving planning and acting, they're going to actually go ahead and compute full dynamic programming updates in the background or some kind of value iteration algorithm on those models and then use those values in some way. So I just have some of those listed here. There's also all this other work on decision time planning. So I told you about background planning because I think it's a great way to be able to let the agent use computation however it can. But there is some cool work actually out there on decision time planning, which means, again, at a state, I'm going to do a bunch of rollouts, for example, and I'm going to make a decision right now using my model based on those rollouts. So model predictive control, there's some pretty cool work from Byron Boots' lab, and you heard a bit about Monte Carlo tree search. Even maybe a little less related, models are being used to improve exploration. There's also this cool work called PILCO, which is mainly using the model to do better estimates of policy gradients. And there's also this work on using models within value functions and sort of to give an inductive bias, where the actual structure of the value function approximator has model components that look like models, but there's end-to-end training to make it so that it's really just an inductive bias in a value function. So I have now run out of time, so I have a few slides in here. If you'd like to know more about these other strategies people have learned models, you can just go ahead through here. I've listed them intentionally so that you could look at them yourself afterwards, but there's some comments here about exploration with models. It is a really big research area. Arguably, most of the work in exploration is with models. And then these implicit planning strategies that I just mentioned, like the Predictron and TreeQN and A3C. I just needed to mention that algorithm name because it's awesome. Okay, so that's really all I wanted to tell you about. We went through thinking about if you had a model, if someone handed you the true model, what could you do? We could go ahead and use all these beautiful algorithms that already exist to learn the optimal policy offline. Then there's a bunch of different questions that actually arise when you're in the online setting and you have to learn the model. Here, I think a very general strategy is Dyna for background planning, and we talked about two really important components there. And then we didn't barely even discuss this last one, but we talked about that briefly. So I'll end it there, and if there's a couple more questions, I'll take those questions, and then otherwise I'll say that's it. Yeah, go ahead.
So if you're focusing on important updates, and this important is defined by the DLR, aren't you focusing on outliers?
Okay, this is a provocative question. The question was, if you're focusing on updates that have high TD error, aren't you focusing on outliers? I think maybe what you're saying is it's an outlier because there was suddenly a really high reward. Let's imagine it's a state with very stochastic reward, or my value function is very wrong, so it's an outlier in that sense as well. I make no claim that prioritizing based on TD error is a good idea. Actually, I don't necessarily think it's a great idea. I think there's probably other ways to prioritize useful samples.
Can this model be used for other tasks, or is it too specific to, like, will it be trained too specifically for this task?
I think you said, can this model be used for general tasks, or is it for this specific task?
Yeah, like we're training models, so we're basically training a simulatory model.
Okay.
Attention on specific tasks. Can this model be extracted and used for another task?
I see, I get the question. So this was sort of pitched as there's one task and you're learning one model for the task, and can you transfer that model to another task? Within the same environment. I am a single task kind of person in that I think there is one larger world with many different things the agent has to do within that world. So here when I say environment or model, the agent is learning a model of its whole complex world. And so I'm imagining the agent is like me. I interact with this very complex world. I might learn little sub-models to solve particular tasks, but they are part of my larger model. So none of this was specific to a single task. It was sort of a framework for AI, really. Oh, let's see if there's any other questions. One second. Are there any other questions? If there's not, I only said I would take two, and then you can just come to the front and ask me more questions. Okay.